The first one, Matt Evans, will talk for an hour or approximately, and then Ricardo DeSalvo will talk for about a half an hour. So Matt got his PhD here at Caltech last year, and he is really responsible for the ability of the first LIGO interferometers to lock up all of the various optical cavities in them. He's going to talk about the locking of interferometers, but he's going to focus on issues of the numerical simulations that play a central role in being able to do that, and also play a central role in debugging the interferometers, which is a process that we're now going through in LIGO 1 interferometers. So, Matt.
Thanks. Okay, I guess you guys already got the who am I part, so I'll skip that. I want to give a brief outline of what I'm going to talk about. It's a little complicated. I have two parts. I'll start with talking about just sort of simulation tools, what we have, what we use to simulate the interferometer, and sort of what we hope to get from it. So start with an example, just sort of a simple one, what goes into an interferometer simulation, and then just sort of a couple of example systems that we've built in E2E, which is our end-to-end modeling environment. Sounds great, but anyway, E2E. Second part is lock acquisition, and first I'll just go through the basics. Some of you have heard this a couple times already. Then I'll talk about sort of the generalization of the basics, which is understanding a sensing matrix and what effect that has for LIGO 1 locking. So what does it lead to? And then this is just actually a couple of plots which are interesting for what happens when you compare the simulation results with something in reality. That was our locking of the first of the interferometers for LIGO, was the Hanford 2-kilometer interferometer. So I'll show data from that. Okay, my three canonical questions that I put at the beginning of essentially every talk. What is it all about? And in this case, what is simulation all about? It's really, we go about collecting everything that we know about the system that we're trying to simulate, all of the sort of the fundamental physics and the parameters that go into it. And we try to organize those things into something which is, I put computationally functional framework. It means something that we can ask to predict what's going to happen if we do X, Y, Z, whatever. But really, it's a collection of knowledge. We try to put together everything we know about the system and then use that understanding to simulate what will happen in the system. Why do I care about this? For the most part, the LIGO pieces, each of them are fairly simple things. They're mirrors. Suspension systems is just, it's a pendulum, it's a bunch of springs, it's masses, things like that. So pretty much the pieces are easy to understand. When you put them together, you get something which is very complex. And without a simulation, you really can't understand what's going to happen there. The back of the envelope calculations become very lengthy. You need a big envelope. Some of the tough problems that we've addressed or are planning on addressing, one is past tense, the other future. Lock acquisition is the second part of this talk, so that's a problem which has been addressed, and the noise tracking is what we're going to be getting to right now. It's sort of the hot topic. We're trying to track down the noise in the interferometers, and we'd really like to be able to use a simulation to do that by putting in the noise sources and seeing how they propagate through the system. And also, we get to then see any noise couplings, things like that, which aren't in the standard sort of theoretical calculations. When I say theoretical, what I really mean is this part. So in the what is known about this, there's a whole zoo of interferometer simulations of one sort or another that are out there. They're little pieces where someone said, I really need to understand this. And they go and they write a little simulation that helps them understand it, and they move on. And there are many, many of these simulations out there. Some of them are frequency domain simulations, and those are for linear systems. If you have something where the input to output response is a linear thing, then you can think about it in the frequency domain. You can write a frequency domain simulation. I put it in quotes because it's not time domain, it's just calculating a response. And those can be very useful, and they are very quick computationally. They're computationally inexpensive things to do. The second part here, time domain simulations, that's what you need when you want to understand systems which are nonlinear. They have some nonlinear behavior, and then all of the sort of the frequency domain analysis falls apart here. And you want to understand these things, you pretty much have to do them in the time domain, and the nonlinear response, whatever it is something that you describe in the time domain. An example of this would be a limiter, something which, or a saturation effect is a way to think of it in electronics. You can put it in an input up to some point, then the output just saturates and won't get any bigger. So that's a nonlinear effect. And these are things that you really need to do in the time domain. A simple system that sort of demonstrates the ingredients that go into one of these simulations is, this is my favorite simple system. It's the Fabry-Pro cavity. It has just 2 mirrors. And so I started over here on the left. We have a laser, we have an optical isolator which lets the beam go through this way, the return beam comes out here. A mirror, I have the blue surface is the coded surface, the rest of it's just to sort of show you that it's a block of something.
Can you just explain how you make the return beam go out one port and the input beam goes in the other?
You're not going to just claim it's magic? You put some clever little fields in there, and you put a polarizer in there, and you rotate the polarization a little bit, and then when it comes back, it's rotated a little bit more, so that one polarization passes through, and by the time it comes back as the other polarization, it comes out the other side.
So the key issue is, it's something we've not paid much attention to in the class, but you have polarization as a handle. And you use polarization as your handle to do something like this.
Absolutely. The polarization in the interferometer is something that's supposed to be well defined. You're supposed to say, okay, once the beam gets into the interferometer, it ought to have exactly this polarization and propagate through with that polarization everywhere. And there are actually noise effects which arise by having a polarization which is a little off or a polarization which is varying. Yeah. This particular thing is a Faraday isolator, is what it's called. That's sort of the description I just gave you. Is magnetic fields and polarizers make one of those things. This is a mirror which transmits a little bit of light through, comes into the cavity, bounces off this mirror, which you can think of as basically 100% reflective. And light circulates, comes back, adds to the light that's leaking in, and eventually builds up if you have the mirrors in the right place. And you get some circulating power here in the cavity. That's just sort of what a Fabry-Pro cavity is. The light which leaks back off of this side comes into the photodetector, and at that point we have a transduction from photons to electrons, and we go down to the electronics part of this system. Here you'll have some analog filters, which I represent by this guy, analog digital converter, some computer which is chunky numbers for you, a DAC on the other side, digital to analog converter, and more analog filtering. Then you go through the next transduction stage, you go from electronics to mechanics type things. In this case, it's coils which push on magnets that are glued to the backs of a mirror, and then you have a mechanics system here. This thing consists of a pendulum, which is this yellow guy here, and a stack. This one is springs and dampers and masses, which try to isolate you from the ground motion. Third transduction stage, you say, it's kind of a cheesy transduction stage, but mirrors themselves are sort of mechano-optical transducers, which bring you back into the optics land. So these are sort of the 3 pieces of a simulation that you need to understand in order to make an interferometer work. I'm going to talk about each of them a little bit separately. So some of the components that go into the optics of a simulation, you have surfaces, which are these guys. Surfaces are, you have a mirror and it has a front surface, a back surface. One's a high reflector, the other's an anti-reflector. They have some reflection coefficient, transmission coefficient. They distort the beam in some way. Media here, I should explain, this also includes vacuum. It's just anything which represent extended space. You propagate from one surface to another. And you get propagation phases, propagation delays, more distortions, things like that. And a bunch of other stuff. You need to simulate a laser, you need to simulate an isolator, you have phase and amplitude modulators, things like that. So these are sort of the components that go into the optical part. And what we like to do in a simulation is represent each component individually, test it individually, and then hook them together to make our simulation out of these sort of simple pieces. A brief interlude before I get to electrical and mechanical components. I talked in the beginning a little bit about frequency domain and linear response. There are a lot of things that are electrical and mechanical which have a linear response. And just because we're doing a time domain simulation doesn't mean we should ignore that fact. So we have sort of a generic transfer function module, which allows us to take any frequency domain representation and represent it in the time domain. You can feed some input in, it'll apply the appropriate transfer function and give you output. So these things are useful for analog filters, digital filters also, anything which has just sort of a linear response. And I'll talk about, this will be sort of the distinction I make in the next couple of slides. Nonlinear components you have to handle pretty much one at a time. You say, I have some saturation effect, I have a slew rate effect, I have whatever, anything nonlinear will be here. So for the electrical components, we think about filters of one sort or another, these guys and the ones that live in here. And other components, there are a fair number of nonlinear ones. these two guys are both nonlinear components. And then analog, saturation, slew rate effects, analog logic, digital algorithms, all those things are nonlinear. So in a simulation, we have sort of this dichotomy of things. The linear ones are all represented by our one generic linear component, and all the other guys we represent one at a time. This makes up the electronics components of a simulation. And lastly, mechanical components, they're all linear. As far as I can tell, I had to think hard for a nonlinear one. I decided the earthquake stops probably counted, but we don't get that far, at least we hope we don't. So pretty much these are just linear things we use our transfer function module. Sure, yeah, the mirrors are, it's just a couple of wires holding this big block of fused silica, and you have stops there which prevent the thing from moving very far, so that if there's an earthquake, it doesn't just swing all over and potentially even fall off. It's just sort of hung very delicately by a wire there. And we learned not so long ago that earthquake stops ought to be very close to the mirrors, because otherwise you can break things. Yeah, learned the hard way. So those are earthquake stops. Despite the fact that I say very close, they're still not within the dynamic range of the actuators. So we don't hope to hit them. That is, you hit the nonlinear effect of the actuators running out of range before you hit the earthquake stops.
The actuators range is like a couple of microns, right?
Something like that, a few.
You speak up, or you repeat questions.
Yeah, the question was, what is the actuator range? And the answer is of order a few microns. I think tens of, but like that. Whereas these things are sort of millimeter type range. Okay, the last bit of this are the transducers, and some of these I had to be creative about. Others are quite clear. We have, I'm not going to read them all to you, but these are all the sort of the various transduction things that we use in order to have the electronics have an effect directly on the optics part or directly on the mechanics. We have here. There are a couple of parasitic ones that people don't think about much. I say parasitic only because we don't like them. Magnetic induction is one. Since we have these magnets there, they will induce currents into anything which is conducting around them. Maybe not important. Radiation pressure is also a relatively small effect, but can be important, especially if you have a lot of power running around in your cavities. So this is just light pushing on the mirrors. Shot noise comes in there.
So can you just define a transducer?
Sure. I have these three kind of realms that I've classified things into, and transducers are things which take you from one realm to the next. Sort of information goes from one realm to the next through a transducer. So I sort of labeled them creatively mechano-electrical transduction, right? It's something which takes you from mechanics to electrical. And here I have just a couple of example systems as they're seen in E to E. This is sort of the environment that we design our systems in. This one over here is the Fabre Pro I showed a picture of earlier. And here's my laser again. It generates a field which passes along this. This is sort of our information passing model. That's how all these things are done. So a transducer is something which passes information to two different types of objects. Here's a mirror, a propagator. This is also known as a media. It sort of propagates a field from this surface to this surface. This one propagates back. That makes a cavity. The return field, my isolator here, is creatively done just by not passing information back that way. I send it into this mysterious control box, which is all the electronics and mechanics for the simplified Fabre Pro I have here. So those are sort of the easy, primarily optical components. The other things are essentially just transfer functions. And then the LIGO optic system is a little more complicated. It looks like this. Once again, we have propagators, mirrors, and then for the corner station, we have a compound optical system. And I'm not going to really get into that too much, but it's just for efficiency. Sometimes we decide that we'd like to represent several mirrors and propagators as a single object. So here we've done that, and we have the vertex station is all this compound optical system. Okay. Conclusion of part one. In simulation, you get to do all kinds of things that you can't do in real life. And it means things like measure a field amplitude directly. You'd really like to know what is the amplitude of a sideband in a particular cavity. In real life, you can't just go and find that. You don't get to know. But in a simulation, you do. You can find out whatever you like, and that can be a big aid to understanding what's going on in an interferometer. Another is adjustment and measurement of absolute positions. We have some basis, which is sitting there on the floor of the LVEA. And in that basis, we get to control the positions of optics, of whatever you like. And those are things that you get to measure then in an absolute sense. You get to know where everything is, and you get to control it also in the same absolute sense, which is something that you can never do experimentally. And once again, it can be a great aid to understanding what's happening in an interferometer. This one is another biggie. When you have a real interferometer, you don't get to say, I'd like to turn off that noise source for a second so I can study something else. Not possible. We get to do that, sort of selectively turn on and off noise sources as we please. This lets you sort of figure out what the contribution of a single noise source is, how important is it, how do two noise sources interact, things like that. The next is asymmetries and imperfections. When you build something, it comes out, as best you can, equal to the spec, but they're never perfect. So you'll have mirrors that have different radii of curvature, things like that, various asymmetries and imperfections. And of course in the simulation you can take them out. You can make two things perfectly identical and thus simplify the problem. So this is all sort of aids to understanding. There's also an aid to development. If you decide you want to develop some new system and you'd like to find out whether or not it's going to work, you can try it first in the simulation. In particular, this one, the lock acquisition stuff was all developed sort of hand in hand, originally entirely in simulation, then confronted with reality, it went through a good deal more development on site, and that would be just sort of trading off back and forth between the interferometer and the simulation. So it allows for really quick, inexpensive testing of anything you'd like to find out and just sort of first order estimate of what effect it's going to have. You can use the simulation for that. And then this is the stage we're at right now. I am currently constructing a simulation which is capable of doing noise propagation and really representing all of the important noise sources, at least the ones we can think of, in the interferometer, so that we can hopefully track down the noise as it's seen there, and by knowing what the noise sources are, aid in their removal so that we'll eventually get the interferometers to design sensitivity. This is sort of the current status of simulation in EDE. So that's it for part one. And I'd like to entertain some questions before I go to part two. No one was entertained enough to have questions.
What are these simulations running on? What development environment are you using?
Pretty much it's all done under Solaris. Some of them...
I mean, is there computer code written in?
It's all written in C++. So it's been run on Linux systems. I don't think it's ever been run on a Windows machine. But yeah, Linux systems, Sun systems.
So what do you mean by detailed noise tracking?
This is where we get to put in things like the DAC noise and represent it as zero crossing blips. Do our best way to represent essentially right down to the level of bit flipping noise that happens in a DAC. And then
what's the DAC?
The DAC is the digital to analog converter. Right? So essentially what happens there is as when you tell it, I want you to put out some voltage, and it has some bits that represent the previous voltage, and it has the new ones, and it just sort of randomly flips them. So when you go from -1 to 0, you have to flip all of the bits. And what that means is you get sort of random outputs on the way through. And this causes a zero crossing glitch that happens, and it's the main noise contributor for, I think, the whole output chain. That's really the largest fraction of noise. So we get to put that in and turn off the other noise sources and look how it propagates through the system. And then say, okay, let's have that on and thermal noise, and see what the bilinear coupling that goes on there. What is it? And really understand those things. So that's first, it's tracking the sources even when they're nonlinear things like glitching, and also then looking at bilinear couplings between noise sources. That's what that's all about. Anyone else? Yeah.
I had a question. Say you wanted to do a simulation for lock acquisition and noise studies, and you wanted to simulate the interferometer running for, say, 15 minutes.
Mm-hmm.
How long does that take to actually crank out a data set? And so say I sit down one day and say I want to simulate 15 minutes worth of interferometer. How long does that take?
Right. The question is about sort of real time to computational time ratio, and the ratio is about 1 to 100, so it takes us 100 times longer than the time you want to simulate. So if we have 15 minutes worth, I can't multiply by 100, but it'll take that much longer. So,
the amount of detail that it begins so fast.
Right. That's for the simulation that was used. It's called HAN 2K simulation, used to lock originally the Hanford 2K interferometer. had relatively little detail in it, and it ran at about 1 to 100. I will say, though, that the most computationally expensive component of that will remain the same in the new simulation. So probably the time scale will be about the same. There's more detail, but most of it's relatively inexpensive computationally.
What is the computationally expensive part?
That little block that I showed with all the lines coming in and out of it, that guy. He's computationally expensive because he has to sit there and raise a matrix to a power and then invert it. And doing matrix inversions is an n-cubed thing, and if n is big enough, this guy can take a long time. So he's the worst of the bunch, despite the fact he's much better than what would happen if I broke it out into 4 little mirrors and 4 little propagators, because then the time scale becomes set by the length of the shortest propagator. And if that's a few meters, then you divide that by the speed of light, and you end up with a very short time step, and your simulation takes forever. So, but yeah, this guy's the worst of the bunch, and most of the rest of the detail, while it adds sort of a lot of richness to the simulation, doesn't take a lot of extra time.
How is the inversion done?
As best I could do it.
I mean, is it using composition or is it something certain?
Yeah, it's basically, you look up in numerical recipes how they did it, find their most efficient algorithm, hack on it a little bit to get rid of the inefficiencies that I could see that are sort of plainly there, and put it in. We found that it was pretty much the best. We tried a couple of standard packages that were out there, and this one was as efficient as any of them. So
what's the method that you used?
It's UD decomposition, I think is right, but it was years now since I put this thing together, so I don't know. Any others? No? Okay. Quick coffee break? No. On to part 2. So lock acquisition, this was really, in some sense, it was an example of what you can do with a simulation package. It was also how I can get a thesis. But, so I needed, the problem was that we had essentially 6 months before the interferometers were coming online, and no one had any really good idea as to how to make them lock. So I sat down with what had already been developed of EDE and started putting together a simulation. I guess I should say first, I'll go down my points here, maybe I'll make more sense. What is lock acquisition? Lock acquisition is, you start with an interferometer that has a bunch of mirrors. I'll consider a Fabry Pro cavity. A bunch of mirrors just swinging around. Okay, sort of swinging in the breeze, they're moving of order a micron, sort of time scale. It depends on your seismic noise, excitation sources, things like that. And you'd like to lock it so that they move together. You guys heard about Pound-Reaver Hall locking and how that works. Essentially, what you want to do is lock these things so that the relative motion of the 2 mirrors is quite small. They can still be doing this, but they can't be doing that. So you get the relative motions down to 10 to the minus 12, above 10 hertz, something like that. Many orders of magnitude less relative motion. And then it's locked. It's being controlled by your control system, which is a bunch of linear controllers, which you guys know all about. You're experts, so like that. Why do I care and why should you? I care, and you should care, because if you can't lock an interferometer, you can't use it for anything. It's just mirrors swinging in the breeze and not much good. Not much of a breeze in a vacuum, but anyway, not much good. So what do people know about this? I was a little distraught to find that at the time I was starting to get into lock acquisition and trying to figure out how to lock the interferometers, there was basically nothing written, nothing published about lock acquisition. There's one paper that I found published about locking a Fabry Pro cavity, but aside from that, essentially no publications on the topic. So if you want to do something simple like a Fabry Pro cavity or a recombined interferometer, which is basically just 2 Fabry Pro cavities, you can do it. It's pretty easy. You essentially turn things on and it locks. If you want to do something more complicated, I suggest you read my thesis, because it's a lot harder. Or listen really carefully right now and you'll get it all. Okay, so once again, back to my favorite canonical system, the Fabry Pro cavity. Same deal. I've put a couple more labels on here. I want to label the field amplitude, which is circulating here, and label this position X. I should go through this really slowly because this is a very important slide. Let's start here. You guys may have already seen this. This is the Pound-Reaver Hall error signal that comes out on reflection. And what it is something which, for small x, relative to the wavelength, is basically proportional times this to the position there. So here's your Pound-Reaver Hall error signal. For x that are very small, it's proportional to x.
So x is the error in the position of the mirror relative to where it should be in its locking.
Right. I have some encoding here. The dot means I'm going to hold this guy fixed, and the x means I'm going to consider this degree of freedom. I'm going to call it x. go over to the graph here. 0 is the point at which you've reached the resonance location. It's really, the round trip phase in the cavity should be 2n pi of, the round trip phase in here is 2n pi. I choose n to be 0 so that I can put a 0 there, and you don't have to worry about things like wavelength too much. What you see here is the power buildup in the cavity as a function of x. It's peaked near 0. The reason why it's off is because the mirror was moving. It's a detail. This is the signal you get coming out. If you look at, you demodulate what's coming out of this photodetector, and you get a signal here. It has a very nice linear section here near 0 crossing. And that's something you can then use to feed into a linear controller, and you have all of the weight of linear control theory at your disposal to hold this cavity on that resonance. So once you're in this region, you're pretty much safe. You've got it worked out. The hard part then is getting to that region. It's about, this is for a LIGO arm cavity, is sort of the parameters in the graph I've given here.
So let's just say explicitly, so the green curve is obtained by RF radio frequency modulating the laser light.
That's right. So you RF modulate the input beam, you lock this on the carrier, the sidebands are promptly reflected, you beat the two together here, you demodulate that, and you end up with this guy. Okay, Convever Hall reflection locking. That's what it is. The width of this linear region is about lambda over the finesse of the cavity. In this case, it means lambda over 1,000. That's what it is there. The finesse of the cavity is actually 300, but there's some factors of pi in there. Basically, lambda over 1,000. So a relatively small region that you have to bring the cavity into in order to use your linear controller to make it lock. So remember this equation briefly. Here I've rearranged it. What I've done is I've said, okay, if I divide by the power term, which was in that equation, that's this guy, so essentially the power circulating in the cavity, I get something which is proportional to x over a much broader range. And I've drawn it as this red curve here. You can compare it to the green one, which is the green and blue were from the previous page. So you end up with essentially a very long linear region. Now it's linear on the scale of lambda rather than lambda over 1,000. So you end up with something that your linear controller can be happy with over a much broader range. And then eventually I say, okay, I can't really measure the power in the cavity when it gets small. This graph is from a simulation, so there's no noise, but in reality, this blue curve gets noisy. You're dividing by it. As it goes to 0, you say, okay, I can't do that anymore. So you just shut it off.
So how do you measure the power in the cavity?
You look at what's leaking through the end mirror. It's not a perfect reflector, so a little bit of light comes leaking through. You measure that, and it's just proportional to the power that's circulating. And then if you take the green curve, you divide it by that power you're measuring, which is the blue curve, or something proportional to it, you end up with the red curve. Okay, so this gives you this nice broad linear region for your linear controller. That's great. What happens when you use it? This is a graph where I've taken the blue one, and this one is x, the position of the mirror. It's sort of the error from resonance. You can think of it that way. And in simulation, I've sent a mirror shooting in towards resonance with a velocity of 3 microns per second. And when it gets to the resonance, the linear controller turns on and pulls it in and locks it. So you see this thing stops there at 0. So that's sort of lock acquisition in action in simulation. This is then the power, is the blue curve here is the power buildup. It's the same encoding as that one for the signals. The power buildup as a function of time in the cavity. So as you bring a cavity in and lock it as its resonance position, the power builds up. And then here we've achieved something stable lock. The controller is now holding the mirrors, and they're locked stably together. So here's lock acquisition for a simple Fabry-Perot. Does that make sense? Questions right there? That's an important part. Yes? No? Good. Okay. So then you move on to a LIGO 1 interferometer, power cycle Michelson. Here, power cycle Fabry-Perot Michelson, I should say. And I have the same encoding of degrees of freedom labeled. The mirrors are the recycling mirror, lights coming in over here, beam splitter, input test masses, and test masses, like this. And then there are 3 signal ports that you look at to get error signals from. Each of those could in principle provide 2 error signals. We only actually use one of them. I may come back to this. Basically the idea is just to say that here we have 4 degrees of freedom and really 5 useful error signals. I put this here in case anyone's actually still concerned about gravitational waves.
So why are there 2 error signals per readout?
For each one of these photodetectors, you can demodulate in either in phase or quad phase. You have a choice of demodulation phases. And from that, you get 2 here, 2 there. This guy, as it turns out, only has 1 really useful signal.
So modulation, cosine omega t and sine omega t.
Exactly. So if you modulate with sine, if you demodulate with sine, it's in phase. If you demodulate with cosine, it's quad phase. So we have, yeah, five signals, 4 degrees of freedom. Should be able to do it. Okay, so for the Fabry-Perot cavity, I had this thing, this sensing matrix is what I'm going to talk about. Essentially, I had this equation for my Fabry-Perot cavity. Here I've just assumed x is much, much less than lambda and taken out the sine part. You can think of this as a matrix equation where I have a 1 by 1 input vector, a 1 by 1 sensing matrix, and a 1 by 1 output vector. And then I can go about doing a matrix inversion, which looks very sophisticated, and arrive at a result where I've just divided by something. I didn't need a PhD to figure this part out. When I say not always invertible, this is something I'm going to generalize. I said that eventually the signal gets too noisy and I can't just divide by anymore, something which is crossing 0 frequently due to noise. And I think I just can't do that division anymore, so I explained where I cut off the signal. What I'm going to consider that as is my matrix is no longer invertible. The reason why I'm writing this in this notation is because it's then easy to extend to something with more than 1 degree of freedom. Here for the LIGO 1 interferometer, I have, as I said, 5 signals and 4 degrees of freedom. So I have a 5 by 4 sensing matrix. I can't invert that straight up. Probably tell that because it's not square. But I can pick pieces of it. And what will happen with an interferometer is you'll essentially look at a matrix and you'll pick the largest piece of it that you can invert. And by inverting the largest piece of it, you get to control the most number of degrees of freedom. And in an interferometer, you start with essentially a matrix which is complete noise. You can't invert it at anything. It's essentially 0 by 0 matrix inversion is all that's possible. And then you progress. In this case, we skip 1. You go to 2. I can invert a 2 by 2 subset. Then I can invert a 3 by 3 subset. And then 4 by 4. And you may rearrange your 4 by 4 as you go along. But the trick is just that. You take this sensing matrix and you select the piece of it that you can invert. And from that, what you're doing is you're selecting some collection of demodulation signals from which you produce some set of error signals for your controllers.
So can you explain the 4 degrees of freedom you're trying to control?
Sure. So the 4 I've labeled here are these guys. Okay, I have position of this mirror, position of this one, position of the end test masses, and once again, this encoding means I'm measuring everything relative to the position of these 2. So those are my 4 degrees of freedom. They're not the 4 canonical degrees of freedom because those are harder to explain. But these work just fine since I'm doing a generalized matrix. So the progression for a LIGO 1 interferometer is like this. You start with, we label these states, we gave the numbers so that it'd be easier to talk about. State 1 could be called state 0. We are controlling no degrees of freedom. The mirrors are just swinging around. And this is the starting point for lock acquisition. State 2, we've jumped immediately to 2 degrees of freedom, and it just so happens that we can get away with that. You're asking for a double coincidence, but it's okay. The resonances for these things are quite broad. It's a low finesse cavity. So we wait for the recycling cavity, those 4 mirrors in the corner, to all come to sort of something that approximates a resonance position. At that point, we can measure a 2 by 2 subset of the sensing matrix well enough to invert it. You start doing that inversion, and it allows you to control 2 degrees of freedom, which are the RM and BS degrees of freedom I showed here. You control these 2 guys. And that gives you control of this part of the interferometer. State 3 happens when one of the arms happens to swing through, just haphazardly it arrives at its resonance position. And when it does that, its matrix element gets large enough, sort of climbs out of the noise. You can then invert a 3 by 3 subset of the matrix. And you can control correspondingly 3 degrees of freedom. The last one, the other arm, is still just sort of swinging around. Eventually, it swings through something, its error signal climbs out of the noise, and you have a 4 by 4 matrix you can invert. So then you're at state 4, you're controlling all 4 degrees of freedom of the interferometer. If you wait a while and you're lucky, you arrive at state 5, where the power of the interferometer has come to equilibrium, and you're basically done with lock acquisition. Now you can switch to detecting gravitational waves. So this is the progression for a power cycle very pro.
4 and 5 are essentially the same.
4 and 5 are not quite the same. 4 is, I got it. Okay, and then you wait, and the power builds up. As it turns out, the 4x4 matrix you're using becomes singular. You have to use a different 4x4 matrix. You use that one for a while. I mean, you go for 4x4, it becomes singular. You use a 3x3, you switch back to a 4x4. It's sort of a complicated thing to get from, I got the fourth one, to, I'm done. Right? In terms of number of degrees of freedom, yes, they're the same, 4. But this state, this is essentially where lock acquisition dies. Frequently in the real interferometer, this is where things will fall apart. So that's why I made this distinction. It's really here you're done, here you're just getting into trouble. So now I've been waving my arms and talking about power building up and things like that. Here I've got real and simulated data. Do I have to tell you? Okay. This is the real data in case you hadn't guessed by the noise. And we start with the red curve is the power built up in the corner part. I said it was the first part that we acquire as we lock that sort of subset of the interferometer. You can imagine that this curve is just flat straight across here, because really it is. And here we've acquired state 2. We've locked 2 degrees of freedom, running happily along. And these are the power in the 2 arms, basically nothing. And at some point, one of the 2 arms locks. And we pick up power in one arm, we've arrived in state 3. You keep trundling along, and if you get lucky, you hit this point where the other arm goes through a resonance, you lock it, and the power in both arms then builds up. You see we've got a couple of order of magnitudes here on this log scale. Orders of magnitude.
How come the power can build up in... How do you keep the power building up in both arms once you only have one lock?
It's not hard. The round trip phase.
Okay, so you're keeping it not quite.
No, it's just swinging around,
oh, it's still
right?
Okay.
And when it goes through a resonance, you see, oh, I've got an air signal, and quick you try to grab it.
You grab it, and I would think that as soon as you grabbed it, the power would start building up.
That's exactly right. So, well, the first one is like that. You pick him up, he locks. The other one's still swinging around haphazardly. That's state 3.
The power doesn't build up very much. It's got another order of magnitude to go.
Doesn't really have to. A lot because it's leaking on the other arm.
Oh,
right. So actually, when you have only one arm locked, most of the power comes right out the dark port. There's an asymmetry there, an opposite sign between the two. So the light's dumping out on your asymmetric port. And then when you lock this one, it becomes a symmetric system again. And then the power can build up in both arms and in the power recycling cavity. And you get several orders of magnitude from that. A couple of orders of magnitude. Here I've shown the error signals we get, that is the deltas essentially, as measured for the interferometer. I'm not going to talk about it much, but just to say that here we're going along, we lock state 2, we have 2 of them are non-zero, they get pulled into 0. This is where we've locked state 2. Here 2 of them go in opposite directions. It's because they're not defined as nicely as I defined them in the picture. Essentially one of them is still 0. These guys are only representing 1 degree of freedom. They have exactly the same value but opposite sign. And then here that we actually get all 4 degrees of freedom. You can see these 2 can now be different. This is the same thing then in simulation. And you'll notice an amazing similarity between the 2, which is purely coincidental. These events are basically random things. They happen as mirrors move about due to seismic motion. So in our simulation, we ran a few simulations, and at one point Hito said, oh my God, this looks just like it. So we recorded this one, and you see the same sort of state progression going on here. It's actually fairly typical. I mean, the order has to be the same, and the durations just happen to be close to the same. So state 2, state 3, one arm lock, state 4, both arms. And then error signals are, again, very similar. This is something that gets back to, I mentioned things that you can know in the model that you can't know in reality. Here we see the positions of the mirrors as they swing about. I'm not going to talk about it, but this is something that you can't measure with a real interferometer. Your best information is just this. So in the simulation, however, you can look at these things and see what really happened there as far as the simulation is concerned. So this is simulation meets reality.
So on the bottom left curve, there's some sort of glitch before the locking into state 2. What's going on there?
So here we're actually losing state 2 in this one, and then basically you shut things off. And then here you turn things back on as the power in the power cycling cavity comes back up. We didn't show the 20 lock losses that came before this event, but there are many. And there are sort of accidents that happen. As a mirror is swinging around, it may resonate some field other than the one you want to resonate a sideband as opposed to the carrier. And when that happens, it destroys the resonance condition for the part of the interferometer you had locked, and you get set back to 0. You start over, work your way back through.
So how many such failed locks do you have in order to get one successful lock?
The number has to be at least 4, and is generally much larger than 4. That is, for each arm, you start out by locking state 2. That's pretty much easy. You've got the PRM locked. Then either arm can go through a sideband resonance and destroy that lock, or it can go through a carrier resonance. If both of them hit carrier resonances first, then you can lock the whole thing. If either of them hits a sideband resonance, you lose it and you start over. So immediately you're at 1 in 4. And if you're missing any carrier resonances, the probability gets worse by the probability that you miss squared. So things get bad in a hurry if you're not locking on each carrier resonance. It turns out that in terms of time, it's not so long. If things are working properly, it'll take you less than a minute to lock the whole interferometer. If systems are not working, it can take you 10 or 15 minutes or all day or whatever.
You don't have any way of knowing and gauge how often it is a carrier resonance or not?
Not really. By the time you get to it, sure. Do you have any way of knowing whether you've encountered a carrier resonance or a sideband resonance in the arm as it's just swinging around? And you have a way of knowing, but by the time you know, it's too late. Is essentially what happens. As it begins to resonate, it's destroying the resonance condition for the part that you have locked. So you see the power start to build up as your control signals are already going crazy. By virtue of the fact that your control signals went nuts, you know that you hit the wrong one, but it's post hoc. If it were tragic, we could probably think of a way around it, but as it turns out, it's not tragic. It's just annoying. So, yeah. Any other questions? Should I move on? I keep on reaching down for this button there. I'm going to skip this one, I think. Yeah, sure. Okay, so conclusions. We have managed to lock all of the LIGO interferometers at this point using this lock acquisition scheme. So it was really a big step once we got the 2K interferometer going. From there, it was just a matter of repeating the same thing at other sites. And some of that was hard because the environment's a little different. But for the most part, locking one is locking them all. At this point, they're all working. So that's great. Lock acquisition is best thought about in the design phase. This is something I say every time, and I kind of feel like I'm harping on the people who made the interferometer. And it's because when it came time to lock the thing, people had, when it came time, to show up at the site and make it work, people hadn't really thought about lock acquisition. And this is sort of a historical thing. People build an interferometer, and they sort of think that the experimentalists at the site will figure out how to make it lock. And I think that's fine. For simple interferometers, that works great, and the guys at the site figure it out, and all is well. For more sophisticated interferometers, and I think that signal recycling and dual recycle interferometers fall into this category, you have to think very carefully about how you're going to lock the interferometer before you finish designing it. So this is sort of a lesson I learned along the way, and hope to pass on.
As we will see if it is good or not, because in real world, because they have a longer wait time for the pipes, they have been thinking on how to
lock.
So if your philosophy will be better or not, we will see with the experiment called Virgo and see if they go right to the result or if they go through the same algorithm.
Or maybe they thought about it too long in Virgo, and the result is that it takes longer to make it work. That could be true. But I have great faith in your suspension systems. So.
What does Tama do?
What does Tama do? Previously, Tama had essentially a recombined interferometer, right? So that makes things easy. The signals separate. You basically have 2 Fabry-Pro cavities. What they've done right now is they have a recycling mirror, but it's mostly transparent. So the recycling factor is, I think, 4. The signals are still separable enough that they can lock it as 2 separate Fabry-Pro cavities and then lock the recycling cavity in, just because it's low enough finesse. My guess is that they're going to have trouble when they get to, they would have trouble when they got to a higher recycling gain, which they will eventually. I say would because I don't think they actually will. They have enough smart people that they'll figure it out before they get there. But But yeah, I think that potentially if they just arrived with their interferometer and with a recycling mirror or recycling gain of 10 or 20, they would have problems there.
Are using so different method of extracting the aerosol.
Right.
For triple harmonic demodulation. So the inventor of that method say that it's easy to work to using that method. So how you don't need so complicated matrix or something.
One way to think about this is if you think about a sensing matrix and you say, okay, let's start out by designing a sensing system which has a diagonal matrix. Then a lot of your problems go away because inverting diagonal matrices is a very easy thing, right? So if you think about it and come to that conclusion and have a way of doing it from the beginning, that's really great.
That would be thinking about it in the design phase.
Exactly. That would be thinking about it in the design phase. So yeah, I think that's true. I looked at some of the sensing schemes, and if you can really just make your sensing scheme inherently diagonal, you've got a much easier job. Yeah? Last point, I guess you probably all read it by now. We're going to be thinking about dual recycling and how to make that lock and what our sensing scheme will be, and hopefully I'll get some words in edgewise before the thing is finished being designed. But that's for future work, probably a future simulation and some lock acquisition work to be done there. I think that's going to be it for me unless anyone has more questions.